right, so let's get started. I'd like to welcome you for the first ALS lecture of this academic year. And it's not only the first ALS lecture, it's also the first in this new room, which is beautiful. And we're grateful to the provost and the dean for helping us having this new space for our conferences. We hope to see you again and again this year. We are going to record this lecture, so we ask you to turn your cell phone off and so that you don't disturb the recording. So it's my pleasure today to introduce our first speaker of the year, Alisa Bokulich, who is professor in the philosophy department. She's also the director of the Department of Philosophy and History of Science at BU. She organizes a very famous post-term colloquium for philosophy of science. And I guess many of you know her work. She works on a range of topics related to the physical sciences, models, data modeling, thought experiments. She has also done work in the history of physics. In 2008, she published a book on quantum and classical physics, and the title was Re-examining the Quantum Classical Relation Beyond Reductionism and Pluralism with Cambridge University Press. And she's edited many other books since then. So one tiny fact, which she called fun fact, I think that's more sad fact, that I learned today while reading her bio, is that she was the first woman ever to be tenured in the philosophy department at BU. So that's actually remarkable, and congratulations, and hopefully many will follow your steps. So today Alisa is going to be talking about constructing time from space, philosophy of geologic time. One more thing, usually we make a break between the lecture and the Q&A, and we have the reception. We've changed this practice. Now the lecture will last for 50 minutes to 1 hour. Then we'll have the Q&A, and the reception will follow the Q&A. Alisa.
Thank you very much. Well, thank you, Edouard, very much for that introduction. It is a pleasure to be here. This is, I consider, the sister institution for our Center for Philosophy and History of Science at BU, which was founded by Bob Cohen, who was a very good friend of Adolf Grünbaum. They went to high school together, and it's interesting that so much of philosophy of science came out of that friendship between them. So it's a great honor and pleasure to be speaking here today. So I'm going to try to just give a broad introduction to the philosophy of geologic time and try to motivate it as being something that's worthy of more attention than it's been given hitherto. So the structure of my talk today will be as follows. I'll start with some preliminaries, which will situate the project in relation to existing work on the philosophy of time in the philosophy of physics literature. Pretty much most of the work in the philosophy of science on time has been focused on physics, which makes sense. And so I'm going to sort of draw a loose analogy between some of the problems that you see related to time in physics contexts and what we see in the context of the geosciences. I'm then going to try to emphasize and motivate why thinking about philosophy of geologic time is important, not just philosophically, but also scientifically, with a number of concrete case studies that illustrate the importance of thinking through some of the foundational problems. And then I'll talk about the two ways that time is conceived in the geosciences and run through the 5 main clocks of geologic time. Then I'll turn to the 3 key foundational problems that I want to highlight today, which I'll call the problem of simultaneity, the problem of clock synchronization, and the problem of missing time. And then I'll draw some general conclusions. All right, so let's get started. So traditionally, as I mentioned, the philosophy of time literature has been focused on physics. Yet, if you think about the historical sciences like evolutionary biology, archaeology, the geosciences, time is of central importance. And yet, it's often sort of out of sight and not really reflected on. Yet, it is something that is very important to think about how it's conceptualized and how it is measured in these sciences. Now, there's been a turn, I think, in the philosophy of science literature on time, from thinking about time in this very sort of abstract context of time in general, to thinking about time as it's conceptualized within particular subfields of science. So, for example, a lot of the literature looks at let's say time in GR, thinking about some of the puzzles having to do with a lack of a global foliation for certain solutions of Einstein field equations, or it looks at time in quantum mechanics and tries to sort out what is the status of the energy time uncertainty principle, or it looks at thermodynamics and tries to solve puzzles about the arrow of time. So I'm going to follow this lead and try to think about time in these specific contexts and what sort of puzzles arise therein. Now, an important distinction that we should be clear about from the beginning is the distinction between time and the measurement of time. So I'll be talking about the measurement of time, but I think that this is not sort of as foreign of a way of thinking about the philosophy of time as it might seem at first. So if you think about how Einstein defined time in his seminal paper, he writes, the time event is the reading obtained by the event at a clock at rest located in the place of that event. So thinking about time through the lens of clocks and how time is measured is quite common. Another distinction that might be important to sort of clarify at the beginning is this distinction between mathematical observation and natural observations of time. So John Singh, in his textbook on general relativity, writes, in thus setting up a basic concept, the measurement of time along the world line of any material particle, we established a chronometry. The observation of this time is a mathematical observation, MO. It would be foolish to inquire the color of the eyes of the observer. And he goes on, if this book is dishonest and confusing mathematical observation with natural observation, it is no more dishonest than all similar. Every branch of mathematical physics has in its cupboard the skeleton of MO is unequal to NO. Okay, so certainly here I'm going to be focused on the empirical rather than the mathematical investigation of time. And as I mentioned, I will organize my discussion as a series of loose analogies between some of the foundational problems we find in physics having to do with time and the foundational problems that we find in the geosciences. And I want to underscore that these are not identities, so this is not the same, I know that. This is just meant as a loose analogy to, I think, try to show there's a richness of foundational problems that we find in the geosciences comparable to what we find in the philosophy of physics. Okay, so let's get started then. Now, why should we care about the philosophy of geologic time? Well, I think it's important to recognize how important judgments about time are. Temporal ordering, coincidence, the rates of various processes, this is fundamental to almost all scientific investigations. Usually we take these conceptualizations and measurements of time for granted, right? We just assume the clocks work and that time is measured accurately. We don't really reflect on the nature of time in many fields. But there are some scientific contexts in which these unreflective habits are ill-advised, and the geosciences is one of those contexts. So here we need to have a concrete understanding about how time is measured in the geosciences and what are the various uncertainties associated with those measurements of time if we're going to draw the appropriate scientific or philosophical conclusions. It's also important because the official scientific representation of geologic time, which is the geological time scale, it sets the temporal framework for studying the timing and tempo of all major geological, biological, and climatic events in Earth's history. So understanding where this geological timescale comes from, the various sources of uncertainty that go into it, is really important for all these studies that depend on and use the geological timescale for answering questions about cause and effect, ordering, temporal coincidence, the rates of various processes. Okay? So it's important for answering questions such as what are the drivers of climate change? There's an increasing interest in paleoclimate studies. Again, understanding how time is measured, geologic time is measured, is important for adequately sorting out questions like the drivers of climate change, the tipping points of various ecological systems, studying the mass extinctions, what were the causes of the mass extinctions, how did they unfold over time. Again, understanding how time is measured is very important for drawing appropriate conclusions in those contexts, and things like the mechanisms of evolution, testing certain evolutionary hypotheses. Time underlies those studies as well. So, and again, despite the central importance of time to the historical sciences, there's been almost no work done in the philosophy of science on geologic time, nor the various clocks used to measure it. The one exception to this is Alison Wiley's work in archaeology. There she's done some really interesting work on time. But in terms of geologic time, which great larger time scales, this is in a largely neglected topic. Okay, so how is time conceptualized in the geosciences? Well, just like we distinguish proper time and coordinate time in physics, in the geosciences, they distinguish relative time and absolute time. Relative time is just a sequence of befores and afters. There's no definite metric, there's no quantification of time, it's just an ordered sequence. Absolute time, by contrast, is what we normally think of, which is a quantified numerical measure of time. It's tied to our calendar and measured, for example, in millions of years before present. So when you're thinking about what are the clocks of geologic time, they can be sorted into which time do they measure. So there are relative time clocks, such as sequence stratigraphy, biostratigraphy, magnetostratigraphy. I'll talk about what those are in just a moment. And there's also absolute time clocks, the radiometric clocks, the various ones that are appropriate, that are uranium, lead, and argon. Astrochronology, I'll define that. And then I have this sort of odd category at the bottom that I'll talk about a little bit more. If there's a relative time clock that can be anchored and traced continuously one-to-one back to the present, it can become an absolute time clock. So an example of this is dendrochronology, tree rings. If you can trace each ring of the tree, correlate it one-to-one with a year, trace it up to the present, then that becomes an absolute time clock, even though if it's disconnected from that sequence, then it would be a relative time clock. Okay. So it's important to think about the type of time that these various clocks measure. So what's the first one? The most important clock of geologic time is the stratigraphic clock that measures relative time. And the key principle that underlies this clock is the principle of superposition, which is the idea that the deeper layers are the older layers. And this principle of superposition is usually attributed to Niels Stenson, better known as Nicholas Steno. Steno's laws, he published in 1669 a work called the Prodromus. But we can actually find an earlier statement of the principle of superposition in the work of Ibn Sena, in the Book of Remedy, in the section on mountains. Now, Steno went to Florence, and in 1665 he was under the patronage of Ferdinand II de' Medici, who was the son of the patron of Galileo, Cosimo II. And so when he was there, he wrote this work, he articulated the fundamental principles of stratigraphy. And it's sort of interesting because these principles of stratigraphy, in addition to the principle of superposition, there's various other principles having to do with how continuous layers are laid down, horizontals, deposition, and so forth. These principles have survived various revolutions in the history of the geosciences. So it's sort of an interesting case of how there's some continuity in this area. And what's also interesting in Steno's Prodromus is that he not only has this idea of the principle of superposition giving us a sequence of time, but also the idea that at each of these layers, we can draw inferences about what was happening at that time. So he says, if certain stratum discover traces the remains of marine animals, it is certain that the sea was at one time in that place. If certain stratum pieces of charcoal ash, it was certain that fire occurred, and so forth. And so this idea that these strata are interesting not just because of the principle of superposition, that they're built up over time, but also because they contain a lot more information that can be used to reconstruct the history of the Earth contained within those layers and draw inference about what was happening then. Okay. So the second most important clock of geologic time is the biostratigraphic clock. This is the clock that forms the backbone of the geological time scale for the Phanerozoic, which is the last 500 million years. It is important for not only sort of providing a relative age of a stratigraphic unit, but also for the purpose of time correlating spatially distant strata. So this can be traced all the way back to the work of William Smith, who drew the first geologic map of Great Britain in 1815 based on the principle of faunal succession, which is this idea that fossils succeed each other in a specifiable order. Smith used this fact that he saw a similar order of types of fossils at two different locations to construct this geological map and represent these different times. Now, what's interesting is that biostratigraphy was used for correlating distant events even prior to the theory of evolution. And some people have introduced this distinction between biostratigraphy and biochronology. So an influential paper by Bergen and Vancouver defined biochronology as the organization of geologic time according to the irreversible process of evolution in the organic continuum. So, so certainly biostratigraphy was used before there was sort of a theory of evolution to describe why there would be this particular sequence over time, but it becomes biochronology once we add that to it. And now an interesting foundational question here, and this is to people who work in biostratigraphy, this is Marie-Pierre Aubry. She writes, evolution provides the arrow of time that is perceived through the unfolding of this diversity. The arrow of time confers upon biostratigraphy its uniqueness. It is the only non-iterative method for relative dating. So here's an interesting philosophical question. Does evolution provide an arrow of time? Can we infer an arrow of time? Several people have criticized this idea that we can't say there's an increase of diversity over time. Perhaps even there's been a decrease. Bilateral symmetry was sort of a reduction, perhaps, in diversity. But in what sense does evolution provide an arrow of time? So again, I think that there's substantive sort of philosophical questions to think about there. So it's a relative time, but it's one that seems to have an arrow to it, an asymmetry to it. Another key concept in biostratigraphy is the notion of a biozone, which is a stratigraphic unit characterized on the basis of its fossil content that's delimited by biohorizons. So this is a cartoon by Ray Troll, Ages of Rock, and these lines here are presumably these biohorizons that define the first appearance of a particular fossil taxon and the last appearance of that particular fossil taxon. So that will define a particular biostratigraphic unit. These biohorizons can be described spatially in terms of the lowest occurrence or temporally in terms of the first appearance datum. And so there's sort of this duality in time scales in the geosciences between rock time and time itself, which is also conceptually interesting. Okay, so these fads and lads are very important in this process of correlating distant events, as we'll see in a moment. Now, even though the cartoon represents these sort of charismatic fossils, usually biostratigraphy is carried out on marine microfossils. So these are the result of these deep sea drilling projects that take these giant cores from the undisturbed sediments of deep sea, and they're using these micro marine fossils, things like the foraminifera and the radiolaria. So if you look at your lecture series poster, you have a picture of a radiolaria right on it. These are the ones, these are the sort of the bread and butter of biostratigraphy, are these organisms. And again, sort of using this to sort of delineate these things ties in with all sorts of important questions in the philosophy of biology, such as the species problem in terms of how do you identify these various species to be able to define these various biozones in order to have this arrow of time to the stratigraphic record. Okay. So the next clock, and again I'm just going to quickly introduce the clocks before turning to the philosophical problems. The third stratigraphic clock is magnostratigraphy, which again is a relative time clock. It's the recording of the periodic reversals of the geomagnetic polarity, which get recorded in the rock record. So the Earth's magnetic field switches its north and south poles, and iron-bearing grains have a preferential direction when sedimentary rock gets deposited or when igneous rock is cooled. And so you get this sort of barcode pattern. So it's a two-state system of normal polarity and reverse polarity, which is represented by the black and white bars. Now, each of these is sort of a unique sequence, again, which can be used to sort of track time in this relative sense. The process by which this happens is actually not very well understood. And the polarity chron, the time interval that's picked out by these widths, is actually something that can range from tens of thousands of years to several millions of years. So they're not regular. So if we could sort of say, well, the geophysical processes that produce the seafloor splitting or the sedimentation rates, if they were linear and known, then we could infer some absolute time from these polarity crons. But typically they're not. And so that's one of the challenges in the geosciences are these interpolation methods where we have sort of certain events that you're able to sort of pin down being key events in the Earth's history, and then you have to interpolate the time in between these events. And often these linearizing assumptions are made but not justified. So for example, if you think about the Mid-Atlantic Ridge, these are diverging tectonic plates. This is seafloor spreading happens at about 2 to 5 centimeters per year, but the East Pacific rise is much faster at 9 to 20 centimeters a year. Again, so you can't draw these absolute time inferences, only a relative time clock. Okay, now many of you were, so why are we fussing with all these relative time clocks? Why not just use radiometric clocks? Radiometric dating, doesn't this sort of displace all these old-fashioned ways of measuring time? We've got this absolute time method that's physics-based. We have equations to describe it. Isn't this all that we need for the history of geologic time? And you can tell by my tone of voice, the answer is no. I'll get to that later. All right, it turns out that there are several different radiometric clocks based on different radioactive isotope and elements, each with different half-lives that makes it more or less suitable for dating particular substances in particular periods of time. The two radiometric clocks that are most relevant to geologic time are uranium-lead. There's actually 3 decay chains, but I'll just focus on one. And potassium-argon, or its improved successor method, Argonargon dating. So beginning with the uranium-lead, here we have uranium-238 as a half-life of 4.5 billion years, which is roughly the age of the Earth. Alpha particle decays, it goes to lead-206. And uranium-lead dating is usually carried out on zircon crystals. Here's a picture of a small zircon crystal over here. These zircon crystals form at extremely high temperatures when magma from a volcanic eruption begins to cool. And the crystal structure of zircon will exclude lead, but it's able to take up the uranium, which seals it within the crystal. And then the uranium that's sealed within the crystal is locked in there, and it begins to decay. So it's like a little preserved time capsule. And these zircon crystals are extremely durable and can survive these billions of years, very long time periods, intact. And so they're a very powerful way of measuring geologic time. The other key radiometric method, this is the second most, perhaps even more prevalently used in the construction of the geological timescale, is Argon-Argon dating. Unlike most radiometric notation, this is not a parent-daughter relationship like the previous case. It's a version of the potassium-argon, that's the radioactive decay. But the idea is that because we have the relative abundances of the potassium isotopes known as a constant, you can use the argon-39 that's radiogenically produced from the potassium-39. And this is produced by a fast neutron reaction, which takes place in a nuclear reactor, can be used as a proxy. And this is a much higher precision method than the potassium-argon method. You don't need to have 2 separate samples, which can raise problems of rock heterogeneity. You have a single sample that you can carry it out on. Much smaller samples can be measured. And you just need to measure the ratio of the isotopes, which can be done much more precisely than measuring the absolute quantities. So the amount of argon-39 gas, radiogenic argon that's produced depends on a flux parameter, because as we said, we're irradiating the sample to be dated in a nuclear reactor. This flux parameter J goes into the equation, and it involves not only the decay constant, which is our lambda, but it also depends, so it's hard to determine this J. So the way that J is determined is by co-irradiating the sample with a flux monitor. And the flux monitor is a mineral who has a known age that then can be used to determine the J value. And so that's, here's the equation for calculating time. In the argon-argon method, we saw a similar equation here for calculating time in the uranium-lead method. Very simple equation that's being used, but as we'll see, it's much more complicated to actually carry this out. The standard flux monitor, the mineral standards typically used is sanandine, which is potassium feldspar that forms in things like obsidian. And it's interesting, taken from a specific location, the Fish Canyon Tuff, which was a volcanic eruption in the San Juan Mountains of southern Colorado. Okay, so we have these 2 absolute time clocks that are certainly very powerful for measuring geologic time. Another absolute time clock is astrochronology. So astrochronology involves 2 components. First of all, it's cyclostratigraphy, which is the study of cyclic variations in sedimentation in the stratigraphic record, and the correlation of those cycles with variations in the Earth's orbit. And so the theory for this was worked out by Milutin Milankovitch. And if you think about the changes in the orbital eccentricity, the precession of the Earth's orbit, and the tilt, there's these very long time scales, for example, at 405,000 years and 100,000 years, that influence the amount of solar radiation on certain parts of the Earth, that influence the climate, that then influence the amount of sedimentation. So astrochronology uses celestial mechanics to calculate what the insolation conditions, what the solar radiation conditions were at various locations, and then try to correlate those cycles with the stratigraphic record. So you see various patterns. Here's the 100,000 year mark cycles, and then the 405,000 year cycles. And you can see this at many different locations around the world. So astrochronology is an absolute time method because you can use celestial mechanics to calculate from today back in time what the conditions were at long times in the past. It turns out that this method can actually only go back about 50 million years because of chaos, right? The chaotic nature of the solar system, the Lyapunov time is limited, and so it's actually harder to go back much further in time. But at least within the 50 million year window, it can provide an accurate absolute time clock. Okay, good. So we've got the key clocks now under our belt. That was hopefully just a quick review in case you weren't familiar with the clocks of geologic time. And all of these different clocks get incorporated together to construct the geological time scale. So here we have the astronomical cycles, and this is the chronometric scale is the absolute time scale from astrochronology, and the argon-argon and the uranium-lead. And then we have the relative time clocks, sequence stratigraphy, magnetostratigraphy, and biostratigraphy. All this information has to somehow, all of these different clocks have to somehow be synchronized and integrated together to produce the geological time scale. And this is, in fact, a very complex process because we have these very different kinds of information about time coming together with varying degrees of uncertainty. It has to be integrated into a coherent time scale with all sorts of quantitative and semi-quantitative interpolation methods. And it illustrates this thing that I call the model-based measurement of geologic time. And the idea is sort of to have an analogy with some of Aaron Tull's work on the standardization of the second through various cesium clocks. He talks about the model-based measurement of time in those contexts. And I think we can extend this to the other extreme from the second to geological time as well. Okay, but I'm not going to talk about this process today, interesting though it is. And I want to get on to these foundational problems. Okay. So the key foundational problems when we're thinking about geological time, I think we can see these in a very loose analogy with some of the foundational problems that we see in physics regarding time. So let's go back to Einstein's 1905 paper, and he introduces this idea, he's introducing the relativity of simultaneity. He talks about there's a clock at point A and a clock at point B, and he says, so far we've only defined an A time and a B time, but not a time common to A and B. Okay, so I'm going to call this the problem of simultaneity. How do we determine that clocks at two distant locations are reading the same time? How do we correlate spatially distant geological or paleontological events as having occurred at the same geological time? But in this quotation, we also see Einstein sort of pointing to another potential issue, which is he says, there needs to be a clock at these two locations. He says a clock, I should add, of exactly the same constitution as that at A. So this I'm going to call the problem of clock synchronization. How do we synchronize clocks that are not of exactly the same constitution? And as we've seen, that's what we have in the case of geologic time. Clocks of very different constitution that somehow need to be synchronized with each other. How do we know that they're reading the same amount of geologic time? Okay, so I'm going to separate out those two problems. Let's take the first one first, the problem of simultaneity. And I'm going to look at each of the foundational problems I'm going to discuss, the problem of simultaneity, the problem of clock synchronization, and then the problem of missing time. We can explore these foundational problems with regard to any one of the clocks that I gave you, right? Each of those 5 clocks can face these problems, these foundational problems. I'm not going to go through all that. I'm just going to take one example from each area, again, to try to give it some concrete meat and show why it's philosophically productive and scientifically productive to think about these foundational problems. So in the case of the problem of simultaneity, I'm going to look at a historical example. So the problem of simultaneity is something that's particularly salient in biostratigraphy. As we saw, biostratigraphy is used to correlate spatially distant strata and to make inferences. If we find this particular fossil at this location and that fossil at a different location, then these two locations, these sediment layers, represent the same time, is the inference that is often made. And certainly, so Felix Grasstein, who this is the book that introduced the 2012 geological timescale, he says, many studies aim to generate an optimum network of fossil correlations thought to embody a reliable and high-resolution isochronous timelines framework. Okay, so we're using these correlations of the fossil content to try to have these isochronous timelines. Okay, now interestingly, from the very beginning, this was a controversial project. So here we see Thomas Huxley, who challenges this idea that we can infer isochronicity from the similarity of the fossil contents. So he grants the principle of superposition. So this is in an address to the Geological Society of London in 1862. So he grants the principle of superposition, that the deeper layers are the older layers. But he questions whether resemblance of a serial arrangement of various fossils in layers at two distinct locations really can be used to infer chronological synchrony. Okay? Now, the term that was used at the time was contemporaneous. And interestingly, Huxley says, what we need is a new term. We need a neologism. We need to open up the conceptual space to substantively examine this question about whether similarity of the serial arrangement of fossils can be used to infer that they were contemporaneous, that they existed at the same time. So he says what we need is some term expressing a similarity of serialization, but that excludes the notion of time. Contemporaneous is a temporal notion, so he didn't want to use that because that sort of biased the investigation from the outset. And he says in anatomy, when a correspondence of position has to be spoken of, the word homology is used. Geology is the anatomy of the earth, so we'll invent the single word homotaxis, or homotaxy, a similarity of order. So in this address, he introduces this new concept into, this new term into the literature, and then opens up the space for this investigation about whether homotaxy implies isochronicity to be explored. So let's look at how he explores this. So he first considers physical geology. And he says neither the similarity of the mineral composition, nor the character, or even the continuity of the stratum, not even the direct continuity, is proof of the synchronism, or even of approximated. Okay, so he's saying just because they are similar rock types, even if they're continuous, that doesn't mean that they were deposited at the same time. And then he asks whether paleontology licenses this inference, and again answers no. Even absolute identity, he says, is no proof of the synchrony of the deposits. While absolute diversity is no proof of the difference of date. So again, challenging this sort of assumption. He follows Edward Forbes, who was the president of the previous president of the Geological Society and a mentor to Huxley, and he cites Forbes' work as saying, in fact, similarity to the organic contents and distant formations is prima facie evidence not of their similarity in age, but actually their difference in age. And he says this is due to the doctrine of single specific centers. So once we have the theory of evolution, we have the idea that species emerge at a particular place at a particular time, then to be the same species at two different locations, they had to migrate, right? And that migration would take time. And so if we find it at one location, another location, that probably means that they weren't at the same time if they were spatially separated. Does that make sense, everybody? Okay, good. All right, good. So he says, with this grand rhetorical flourish, for anything that geology or paleontology are able to show to the contrary, a Devonian fauna and flora in the British Islands may have been contemporaneous with the Silurian life in North America and with a Carboniferous fauna and flora in Africa. Okay, so he's really undermining this whole sort of project of how it is that we establish this global synchrony of these different geological time periods and be able to say that they represent, can be found at all these different locations around the Earth. Okay. Now, I think his position here is not so much skepticism as a sort of agnosticism, right? Agnosticism, of course, was another term that he coined. And what he wants to say is that we need to develop some tools to resolve this problem, right? We can't just assume it. It's not something that we can automatically infer. It's something that has to be substantially defended. And so this is actually a problem that sort of has continued forward in time to be a worry. It's picked up a century later by David Kitts. that is referred to as a metageologist. It's kind of a curious figure. So David Kitts actually got his PhD in paleontology at Columbia under George Gaylord Simpson, the famous paleontologist. And he taught geology in, I think, Oklahoma or something like that. But he spent a year visiting the philosophy department at Princeton, working with Hempel, and thinking about how philosophers of physics think about time, and that influenced the way he was thinking. He was also influenced by the work of Reichenbach and Grunbaum, and he cites as well as being an influence on his thinking. So it's an interesting story. And that earned him the nickname metageologist. Okay, so he picks up this theme again in this paper on geological time. And he says, he uses the notion of biological signal propagation. So he says, intercontinental correlations invariably invoke biological signals, but we have reason to suppose that biological signals have relatively low velocities, that these velocities can vary greatly from signal to signal, and that the velocity is far from constant. And furthermore, there's all these questions about direction of transit. So this idea that if we think of the geographical dispersal of a taxon, this can happen. There's some taxa that might disperse very quickly and become global quite quickly. There's others that may stay very local to a particular location. But certainly biologists are interested in these sort of questions about, which way did the migration happen? Is this a taxon that could be used for establishing isochronicity, or a taxon that could not be used for establishing time slices? Okay, so if we are interested in using biostratigraphy, the fossil contents, or similarity of serial, the homotaxy, to try to establish isochronicity, what we need to do is try to sort out which of these taxa are isochronous and which of them are diachronous. Okay, so which are the ones that disperse quite quickly and which ones are slower? So this becomes then a scientific problem to try to sort these sort of things out. Okay, so can we distinguish these things? Well, there's different sorts of solutions that have been proposed to this project. So at first it seems, we start with Huxley, it looks like this unsolvable problem. How could we possibly make these sort of inferences about isochronicity just based on the fossil content? We have this idea, sort of thinking about it in terms of geographical dispersal and signal propagation. And if we're trying to use a method that's internal to biostratigraphy, then this proposal by George Scott is one partial solution to this problem. Okay, so he says the amount of potential diachronicity between two distant homotaxial sections is inversely related to the stratigraphical spacing. So the closer the homotaxial events are in stratigraphical space, the less they wander in time. So his proposal was, what we need to do is increase the density of these bio-events to try to sort out which are the isochronous taxa and which are the diachronous taxa. So he says, thus, a major objective of biostratical research should be to make tests of homotaxis more rigorous by raising the density of the events. Okay, so here's a picture to sort of see how this happens. So the sort of bio-events they're interested in are these, first appearance datums, last occurrence datums that I talked about before that just define these horizons, biohorizons. So let's imagine that we have two distant strata. So here's a section of strata A, a section of strata that's some distant location B, maybe halfway around the world, whatever it might be. And we have these three taxa, these three species, the circle species, the square species, and the triangle species. And when we first do our investigation, we say, well, these seem to define these planes of simultaneity, right? It seems that these are isochronous biohorizons between these two distant strata. But if we say, well, we can't rest content, right? As Huxley warned us, we need to think about, perhaps increasing the density of events, as Scott proposes. So we look a little bit more, and we find species star. Okay. Now, notice that we have circle square star here, and we have circle star square here, right? So this indicates that there's a diachronous species here, but we don't yet know which one it is, right? It's either the square species or the star species is not defining a plane of simultaneity. So again, how do we solve this problem? We further increase the density of bio-events, and we find taxon heart. And with taxon heart, what can we infer is most likely the diachronous species? Pop quiz. Square. square. Good, thank you. I was hoping that wasn't going to be a hard question. Good, okay, so square is most likely, right? It's not absolute proof, but it's most likely to be the diaconus taxon. So it's not a good taxon to use for defining, for correlating, temporally correlating spatially distant strata, right? So we're going to exclude that taxon when we're trying to synchronize these distant locations. Okay, good, so hopefully that's clear. So the square would have had a slow rate of geographical dispersal. Okay, now that's a solution that's sort of internal to the project of biostratigraphy. Other solutions require going outside of that methodology, and one solution involves clock synchronization. So it involves synchronizing the biostratigraphic clock with the magnetostratigraphic clock. So remember we saw the geomagnetic polarity reversals. These are global events, so they happen globally, right? It's not, there's no concern about the signal propagation for polarity reversals. And it's essentially instantaneous, at least on geological timescale. It's not actually, it actually takes a couple thousand years, but it's essentially instantaneous. And so these are ones that we can think of as being defining isochronous times at distant locations. So they're not time transgressive. And what we can do then is we can use the magnetostratigraphic clock in order to help sort of constrain the biostratigraphic clock as a way of sort of helping us figure out what are the times that are the same, and that can help us constrain. So what's interesting is that we can have the magnetostratigraphic clock, we have also a problem here identifying what is the reversal pattern is unique. Remember, it was a relative time clock, so we have a unique pattern, but it's not often clear what section of that pattern that we're within. Biostratigraphy can come in to help us sort out which section of the geomagnetic polarity scale, time scale we're in. And similarly, then, the geomagnetic polarity time scale can help us resolve the problem of diachronicity in the biostratigraphic clock. So the idea is that by synchronizing the biostratigraphic clock and the geomagnetic clock, the magnetostratigraphic clock, they each kind of address the weaknesses of the other clock, right? So the biostratigraphy being a unique asymmetry, remember we had the arrow of time, allows us to pick out which section of the black and white bars we are in, and then those bars define isochronous timelines and allow us to then pick out which are the diachronous species and which are the more isochronous ones. Okay, good. So these, in fact, get integrated into what's called it's a giant word, integrated magneto-biochronologic timescale, IMBS, put together. So we can start to see how these things get synchronized together to construct these larger timescales, eventually the geological timescale. But so far, these are just relative time clocks. Okay, good. So, all right. We've seen the problem of simultaneity. We've looked at it in the context of one clock, the biostratigraphic clock, and we looked at sort of what resources it had to solve this foundational problem, and also how going outside of that clock was a way of further solving some of those foundational problems. This brings us then to the next problem, which is the problem of clock synchronization. Okay, so we already saw that clock synchronization was part of the solution to the previous foundational problem, but clock synchronization itself has a number of problems. And so I want to look at it in the context of the radiometric clocks, because we sort of have this view that these radiometric clocks are absolute, they're physics-based, they're fundamental, there's no problems with them, so the synchronization should be very straightforward in these sort of contexts, and it turns out that's not the case. Okay, so when radiometrics methods were first introduced, it was thought that they would quickly replace all other methods for measuring geologic time. Quickly it was realized that this was not the case, that in fact the dates that you obtain from a radiometric clock need to be distinguished from the age. And so you might have thought dates and ages are the same, but the idea is that the radiometric methods, the radiometric equations, the T that we solve for is a date, but a date needs to be geologically interpreted to become an age. So we are sort of introducing this distinction between dates and ages. As I mentioned, Wiley's talked about this in the case of radiocarbon dating, which also has a similar problem. I'm happy to talk about in the Q&A later. Okay, so we have this distinction that we can't assume that the dates obtained by radiometric methods are the true ages of materials. And we can see this in the geological context. There was an emergence of, and this is a quotation from some geochronologists, they say there was an emergence in the late 1990s, so quite recently, an apparent crisis in high-precision geochronology stemmed from published differences between the results of different radioisotopic methods, or the same methods measured in different laboratories for the same critical samples and events in Earth's history. So the increasing demands of these paleobiological studies and paleoclimate studies sort of resolved these time events, sort of revealed that there's an accuracy in radiometric methods, and this has precipitated a crisis. So we'd have two methods, the uranium-lead method and the argon-argon method, dating a particular sample and coming up with two different ages, two different dates. Or even the same clock, uranium-lead coming up with two. Okay, so again, I continue on. So this is the paper that sort of identified the crisis. They note that improved techniques and instruments for measuring isotope ratios have reduced measurement errors to the point that analytical precision is often less than 0.5% of the age, in some cases better than 0.1%. So this is not a problem of precision, right? So the methods of the laboratory they're highly reproducible, there's high precision, they're very repeatable measurements that they're making. So this is not a like sloppy lab contamination sort of problem. Instead, it's a problem with accuracy, okay? So that unfortunately, accuracy has lagged behind precision in many radioisotopic dating methods, okay? So again, we have to think about how do we understand the notion of accuracy in these radiometric methods? And we don't have access to the true values, so how do we think about the distance from true values? Lots of interesting questions there. And then again, another quotation, you would be forgiven for thinking that the analytical uncertainties in published radioisotopic dates would be sufficiently large to encompass the true geologic age in question. Yet research in the past decade and a half demonstrates that this often held assumption is not always true. Okay? So this idea that these radiometric methods have certain uncertainty estimates associated with them, and they ended up revising the radiometric, interpreting a different age for the radio dates, and those were outside of the uncertainty estimates of the previous age. Okay, so how does this happen? So how can we make sense of this crisis, and how did they address this problem in the subsequent high-precision geochronology revolution? Well, it helps to look at a concrete case of this. So one of the prominent examples that sort of precipitated this crisis of clock synchronization of radiometric methods was the problem of dating the Permian mass extinction. So the Permian mass extinction was even worse than the end Cretaceous mass extinction that wiped out the non-avian dinosaurs. So it's the big, they call it the Great Dying. Was it like 96% of all marine species were wiped out, some 70% of all terrestrial vertebrates were wiped out, some 86% of all genera were wiped out. It was like a drastic pruning of the tree of life. Okay, now understanding the timing of the Permian mass extinction, as well as the various geological, biological, and climatic events around it, is critical for establishing cause and effect relationships, right? So we want to know what caused the worst, most devastating mass extinction in Earth's history. This is an important question. We want to not have it happen again, especially not in our lifetime. So we want to establish cause and effect relationship. We need to be able to resolve time. We need to understand uncertainties and how time is measured in order to answer these important scientific questions. Okay. Now, it's also something that's important for the geological timescale. So the end Permian extinction marks the end of the Permian period and the beginning of the Triassic, and the end of the Paleozoic era and the beginning of the Mesozoic. So getting a precise age for that is very important. And you think very happily, the Permian-Triassic boundary is actually really well preserved. And it's unique because, so this is in a particular marine strata in the Meishan section of South China. It's unique because it hosts both a rich pre- and post-extinction biota, abundant volcanic ash beds that can be used to constrain the timing and rates across the boundary. Okay, so the Permian mass extinction in this section of China is like the prime case where you really expect these dating methods to work. We've got lots of material to work with. We have clear, fossil record. We have clear ash records. We use these various radiometric methods. It should work here. Okay, and they're interested in having a precise timing. One of the prime suspects in the Permian mass extinction is a large igneous province known as the Siberian Traps. And so they wanted to date both the extinction events, the pattern of extinction, and this volcanic activity, and see whether or not they could be used to establish a causal connection between these two things. And so in the mid-1990s, they radiometrically underwent this project to date them by both uranium-lead and by argon dating. And this is where we get that quotation from about the two clocks not agreeing. Okay, so Paul Wren at the Berkeley Geochronology Center writes, that we've dated the mass extinction very precisely by Argonargon methods at 250.0, and enabling a conception with the massive volcanism, also dated by Argon methods at 250. Great, those look like they agree within the uncertainty bounds. These same two events have also been dated by uranium-lead at 251.4 plus or minus 0.3 and 251.3 plus or minus 2 million years ago. So there's sort of good news and bad news, right? So the good news was each of these radiometric clocks showed the synchrony of these two events, but the two radiometric clocks disagreed with each other. Okay, so there's a problem, at least with one of them, or maybe both of them, right? That's certainly a possibility too. And so this is what sort of led to this crisis. It turned out that when they tried to just say, well, let's just forget one of the clocks, let's just look at the uranium-lead clock. It turned out, as shown in notes, the Permian Triassic boundary, and this is 2014, has yielded 4 different non-overlapping ages in the last 14 years for the same stratigraphic section of Asian China. Okay, so even the gold standard radiometric clock, the uranium-lead clock, has these 4 different non-overlapping ages. Okay, so again, we have the problem of clock synchronization, not just for these different clocks, right? But we also have the problem for clocks of the same constitution, namely the uranium-lead clock not agreeing with each other. Okay, so again, paying attention to these sort of cases is important not only for solving these questions about the cause of the Permian mass extinction, but also for understanding these ways of measuring time and the uncertainties associated with them so that scientists and philosophers who build on that scientific work can draw the appropriate conclusions. So one of the fundamental assumptions of the radiometric methods is this idea of closed system behavior. So remember I talked about the zircon crystals that would exclude the lead but take up the uranium and seal it within it. Well, as you know, some packages are better sealed than others, and so you can have this problem of lead loss where some of the accumulated radiogenic lead leaks out, which would make, when you date that crystal, appear younger, right? So if it wasn't properly sealed. There's some ways of detecting these losses, so not all hope is gone. There are various Concordia ways. It can be difficult. You can also try to eliminate the damaged crystals. So the high-precision geochronology revolution instituted some new methods that moved from mechanical abrasion to chemical abrasion methods to try to break apart any compromised packages and make sure that they were really getting a closed sample. Okay, so they did this, and again, they were able to improve some of these. Another source of geological complexity that arises is known as inheritance, which is when older zircon crystals are able to survive the volcanic eruption intact. So the thought was that we're dating the volcanic eruption, but if these crystals can survive the volcanic eruption, then they could be much older than, in fact. So this would bias the dates as being older than they actually are. And some research on the formation, the growth patterns of zircons suggests that they can crystallize tens to hundreds of thousands of years prior to their eruption. Again, sort of thwarting these questions about what is it that they're dating. And so, I think this raises important questions that simple methods aren't simple in a geologically complex world, right? We have a physics-based method, a simple equation to solve for time, but you have to realize how that gets instituted in a geologically complex world, and it's far from simple. And so we need to be aware of those uncertainties when we're drawing inferences about the coincidence of events or the time ordering of cause and effect in events in geological history. Okay, so that was just an example of the uranium lead. Sean sort of talks also about some interesting things having to do with how to deal with this geological complexity. So if you get this scatter of dates, right, you have the zircon crystals, some of which seem to be younger, some of which seem to be older. You have to somehow take that scatter of dates and interpret from an age. Again, this distinction that sort of the measurement indication is not the same as the measurement outcome. We have this conceptual notion in metrology that you get a reading on your instrument, but then you have to sort of interpret that as a measurement outcome, and that's a further level of inference that involves all sorts of background assumptions. So the date is sort of our instrument reading in this case, and then we want to interpret a geological age from it, which involves sorting out these questions about closed system behavior and so forth. So he explains then how researchers can arrive at these different ages. So he says those who think a combination of lead loss, inheritance, and analytical scatter are the most important source of error will extract the most statistically equivalent population of zircons and apply weighted means. So we'll use certain statistical methods and sort them out if you think certain biases are the prevalent ones in a particular case. But those who consider pre-eruptive growth of zircon or a significant reworking of ash material after eruption and deposition as the sources of spreading dates focus on the youngest grain or the subset of grains and use those to date. So you can start to see how you get these non-overlapping ages in uranium-lead dating. Now, uranium-lead dating is the gold standard of the radiometric methods, right? It has the highest known, the best known decay constants and so forth, and yet we can still see how in a geologically complex world, these radiometric methods have various sources of uncertainty that need to be taken into account when engaging in these projects about causation and so forth. Okay. Now, what about the Argon-Argon method? The same sort of problems arise here as well. So the Argon-Argon method, remember they also were used to date the Permian extinction. They were systematically younger from the uranium-lead by about 1% or 2 million years. And the proposed explanation was uncertainty in the value of decay constants. So again, this is another important source of error that we often don't think about. So research by Kwang Min et al. In 2000, they noted that it depends, remember, on the relative abundances, as I talked about when I introduced this method, being a constant. Even though it's still believed to be a constant, the value of the ratio has been revised, and so we've got a more precise value of that. Other relevant constants for calculating the decay constant of potassium have been revised, including the atomic weight of potassium, Avogadro's numbers updated, and the previous value of the decay constant, then he argued, should be changed. And I think this understanding the sources of error, the synchronization, looking at the problem of synchronization, is forcing us to sort of look at how these radiometric methods work, the sources of uncertainty that then are important for drawing correct philosophical and scientific inferences. And this sort of illustrates this lesson that physical constants, physical constant is constant, right? It's just out there. It's not handed down a priori, and that their empirically determined values can be, despite their name, inconstant. Right? So these decay constants are something that need to be determined empirically, and we can be wrong in how we determine them. And there's this process of trying to reduce the errors and these physical constants. So just because it's a constant doesn't mean it's absolutely certain. I have to think about how we arrive at the values of those constants. Okay, good. Another source of uncertainty, the Argon method, one was the decay constants. The other was, remember we said it had to have a mineral standard that was co-radiated, and you had to know the age of that in order to determine the flux monitor. So in the Argon method, Sanandine from the Fish Canyon Tuff was what was used. It was a very high precision, but determining the accurate age is proven difficult. So they had to figure out different ways. Well, how do you determine the age of the monitor, right? Which is used in determining the age of your unknown sample. First principle measurements were difficult to carry out. You couldn't extract the argon gas from the viscous potassium feldspar melts. It was proposed, well, maybe we should reduce the uncertainty by intercalibrating it with a uranium-lead clock, right? So we want to bring these two, synchronize these two together, but if we force the synchrony, right, by intercalibrating, they're no longer independent. And the geochronologist said, this is paying too high of a price, right? We could get our clocks to agree, but it would be by force, right? It would be by fiat. And when you're trying to reconstruct events in the deep past, the sort of consilience of independent lines of evidence, this ability to sort of, triangulate these various methods, it's important to keep them independent from each other. Also, we saw that there's a question about, are they representing the same geologic event, right? We could try to synchronize the uranium-lead and argon-argon, but the uranium-lead might be doing the pre-eruptive growth of the zircons, which is a different event than the eruption that the argon-argon. So they may not be representing the same geological event. And in fact, volcanologists are really interested in the difference in dates because it tells them a story about how zircons are formed in the magma in this cycle. So it's actually a source of scientific knowledge that the dates don't agree with each other. So intercalibrating has a price to pay, right? And geochronologists have to raise this question, is it worth paying that price of intercalibration or not? Okay, so they decided it wasn't in the case of uranium-lead, and they decided to intercalibrate the argon-argon clock instead with astrochronology. So here's the study that described that process. So it says, we compared the astronomical and argon-argon ages of tephras of the marine deposits to date, calibrate the age of the Fish Canyon Sanandine, the most widely used standard in argon-argon geochronology. And they said this calibration results in a more precise older age of 28 point for the mineral standard, the FCT, and reduces the argon method's absolute uncertainty from around 2.5 to 0.25%. Okay, so they say, look, we get a great improvement in the accuracy of the argon-argon method, by calibrating it with a stratigraphic clock. And I think that's kind of ironic, right? That here we're using a stratigraphic clock to increase the accuracy of a radiometric clock. So it intercalibrates these two together. And again, I think this illustrates the lesson that these radiometric methods are not autonomous, right? That they depend on all of these other methods that we thought initially they would displace, but these stratigraphic methods are still important for sort of sorting out and appropriately interpreting the geology that goes into these methods. Okay, good. So just to give you a graphic representation, so this is just for the Argonargon dating. We have the age of the Fish Canyon. This is the mineral standard. And then we have the lambda, which is our decay constant. And we talked about the different values, and we can see how we get different ages, right? Depending on which combination of which decay constant value we use and which age for the mineral standard, how these ages vary. Okay, so what they decided to do was to take the min version of the decay constant and the Kuiper, which is the Astrochronology quote. So the yellow one is the one that was actually decided on. So there was a quorum of Argon scientists who got together and they said, we're going to vote for synchronizing the clock with the Astrochronologic clock and use those values for the Argon dates. Okay, so they did that. This brought the clocks into closer synchrony. One of the journal lessons, I think, from these stories is that these radiometric measures of absolute time aren't exactly absolute. Okay, so they brought these two together. Synchronizing the Argon clock with the astrochronological clock actually was able to close part of the gap with not all of it, and maybe it's a good thing not all of it if they represent different geological events. But this revision, this decision to use this new 2000 value of the potassium decay constant and to use this new mineral age intercalibrated with the astrochronological clock led to 1/4 of the boundaries of the geological timescale being revised. So relative to the 2004 geological timescale, 26 of 100 timescale boundaries changed age, of which 14 changed by more than 4 million years, and 4 changed between 6 and 12 million years. So this synchronization, this clock synchronization, had a huge impact on the geological timescale. It again sort of, I think, understanding how time is measured and understanding the uncertainties is important for what attitude we take towards the geological timescale. As I said, this geological timescale sets the temporal framework for all of these paleobiology and paleoclimate studies. And if we don't understand that it is a dynamic work in progress, the geological timescale, you might have thought the boundaries of the timescale, the geological timescale, are just fixed by convention, right? Or if they're not fixed by convention, they're just radiometrically dated. And it turns out that it's a lot more complicated, the story. So the geological timescale is a work in progress that's always changing. The changes can be quite dramatic in some cases. And it also creates the problem of legacy data. So if you're, let's say, a paleontologist who's looking at dinosaur lineages, and you're looking at Argon dates that were prior to 2012 and Argon dates that are after 2012, they can't be compared. They use different decay constant values and different mineral standard ages. And so they're not comparable, right? You'll get bad results to your study if you don't realize this process of how these changes are made to radiometric methods. If you just take the radiometric date as the true age, you'll be led astray without understanding this. So again, the issue of legacy data is an interesting one as well. Okay, good. So, I've talked about two of the foundational problems so far, the problem of simultaneity in the context of the biostratigraphic clock, the problem of clock synchronization in the context of radiometric clocks. I now want to turn to the final foundational problem that I want to discuss today, and that is the problem of missing time. And the problem of missing time is really a problem that sort of underlies or potentially thwarts all of our clocks. Here's again, there's often an assumption that the stratigraphic record is essentially continuous and that a one-to-one relationship exists between stratigraphic sections and the temporal interval they cover. This is often an assumption that's used in these biostratigraphical studies of these deep sea core, sediment cores. But there's a growing recognition that there are many gaps. And some have said, well, maybe there's even more gap than record. So what we need to do is think about how complete is the stratigraphic record? How much time is represented? Are there gaps? Is there missing time? Okay, so a gap in the stratigraphic record is called a hiatus, and there's two different kinds of hiatuses. There's erosion, which is the idea that there was sediment deposited during a time interval, but it was subsequently eroded. But there's another possible hiatus, which is stasis. And that's where nothing happened, right? There was no sedimentation and there was no erosion, okay? And these are importantly different from each other. They're both going to lead to gaps in the stratigraphic record. But they're different. Now, what's interesting is that the erosion hiatus was sort of assumed to be the default for much of the history. And it's only just quite recently that some stratigraphers are starting to argue that perhaps stasis is much more common in sedimentation systems than we previously thought. So Tipper says here, for almost all the time, almost everywhere, in almost every sedimentation system, nothing is happening. Astoundingly, this predominance of stasis in sedimentation system is not documented by geologists or even commented on. And so he draws this analogy to Gould and Eldridge's punctuated equilibrium. And he says, look, here's a quotation from Gould and Eldridge, they say, no bias can be more constricting than invisibility. And stasis, inevitably read as absence of evolution, has always been treated as a non-subject. Most evolutionary biologists assumed continual change as a norm, didn't even know that stability dominates the fossil record. So this idea of the invisibility of stasis, right? So you sort of have these frameworks that guide this research, that there's always something happening, right? And this idea that, well, maybe there's periods where there's nothing happening, were not investigated, even though they're very common, and when you sort of have that category, you can see it happening everywhere, or not happening everywhere, as the case may be. But it's something that wasn't scientifically commented on. It was sort of invisible to scientific research. And so there's an interesting parallel between those two cases. Okay, so a very recent paper this year, Chris Powell at the University of Minnesota writes, the question of whether time gaps, hiatuses in the stratigraphic record, mostly record erosion or stasis, is fundamental not only to understanding how the Earth records its own history, but also for thinking about how much time is represented in the strata. The fact that during stasis, time recorder is set to pause rather than erase leaves open the possibility that information may still be preserved, even if in the most tenuous of ways. Okay, so thinking about this problem of missing time, what kind of hiatuses are in the record, where are they, how long are they periods of stasis, are they periods of erosion, is important for answering this question of how to construct time from space. Okay, so how is it that the problem of missing time can sort of undermine these clocks of geologic time? So I'm just going to give one example of the magnostratigraphic clock. Hiatuses are, as we said, are gaps where there's not sedimentation, sort of recording in that period of time. And so if you think of, here's a seafloor core, you have these polarity crons, so you have your different normal polarity crons, A, B, C, and D. These are your stripes, and then you have the white reverse polarity in between here. And what you can see is that if there is a hiatus in time, namely a period where there isn't sedimentation happening, what can happen is that two of the polarity crons can get sutured together, right? So C and D will look like a single polarity cron, right? And remember, it was important to be able to count backwards and recognize where in the barcode pattern you were. But if there's hiatuses in the record, missing time, then your barcode pattern can get corrupted in various ways, right? So that can happen both for the normal, and here's an example of a hiatus affecting suturing the two reverse polarities. Okay, so you can see both. This is the problem of missing time is very important for thinking about how these clocks measure time and the uncertainties associated with those clocks. Hiatuses in biostratigraphy can mimic diachronicity, so they're important there. Hiatuses in astrochronology can undermine the correct identification of the cycles. So the problem of missing time is also going to undermine these astrochronological cycles, where we're saying there's cycles of sedimentation that are correlated with astronomical solutions. We're missing a cycle, right, due to stasis or erosion. We're going to miscorrelate these two things. That miscorrelation is also going to affect the Argon clock, right, because we use the astrochronology to date the standard that was used in the Argon clock. Okay, so the problem of missing time, again, is very important for thinking about how time is measured. Now, what's interesting, again, is to think about how do you make visible missing time, right? So Tipper, remember, talked about how this was something that was invisible. The idea is that we need a method for representing. Normally, the sequence stratigraphy just draws depth and the different stratigraphic layers, and they'll note an unconformity, but we don't know how long that unconformity, how long that gap was. There's something weird that happened there, but how long is it? And interestingly, in a paper, Harry Wheeler introduced in the 50s this idea of using space-time diagrams. And the idea is to try to represent time in our representation of the stratigraphic record and make visible these periods of hiatus. So here's time as the vertical axis instead of just depth. So he says concepts largely troublesome because the temporal factor is a fourth stratigraphic dimension. He says the vertical dimension in these pictures has to be shared by both thickness of the rock and by time, but they're mutually variable, right? We can't just assume that depth is equal to time. Thus, dawn, deposition, erosion, other events can only be represented because geologists have not succeeded in developing means for the graphic portrayal of a space-time continuum, time area section. So he introduces these space-time diagrams. And again, this idea of how do you sort of have these tools within a field to make visible these periods of stasis. Okay. So getting close to the end here, so here's our friend Chris Spink. So come back to one of our analogies. He writes, questions about the nature of time are transformed into questions about matter filling the universe and how it moves. I think we see a loose analog of this also in the case of the clocks of geologic time and thinking about the problem of missing time. There's the importance of going 3+1 dimensional. So again, Paolo, the record of time is even more complete across even longer time scales if we measure in a three-dimensional perspective. So typically we've just measured this vertical column, right? How deep it is, right? We've had this one-dimensional picture of time from space, only in one dimension. And what we're realizing is that if we want to really construct time from space, we need to move beyond the one-dimensional picture to a three-dimensional picture. We need to think about how the sedimentary processes move matter throughout space in 3 dimensions. And if you take a three-dimensional view, there's a lot more time recorded than would be recorded in a vertical column. And so we may actually be able to address the problem of missing time by going three-dimensional. So many important sedimentary processes are dominated by lateral sedimentary accretion, give several examples, and substantially more time is elapsed represented in preserved sediment in 3 dimensions than relating to a vertical accumulation. So in constructing time from space, we must consider not just the one-dimensional vertical depth, but rather examine how sedimentary processes record time in full 3 dimensions. Okay, so just to conclude then, we've traced this loose analogy between problems in the philosophy of time and the philosophy of physics literature and the philosophy of geologic time. We looked at 3 problems: the problem of simultaneity with the example of the biostratigraphic clock, the problem of clock synchronization with the radiometric clock, and the problem of missing time in the stratigraphic clock. And what I hope I've convinced you of is that the philosophy of geologic time is not just philosophically interesting, but it's also scientifically important. A concrete understanding of how geological time is measured and the associated uncertainties is important for drawing appropriate conclusions about a range of projects, such as those in paleobiology and paleoclimate studies, which look to unravel the drivers of climate change, the tipping points of ecological systems, and the mechanisms of evolution. So, thank you.